Ever wondered how robots learn to handle complex tasks, like picking up a cup or assembling parts, without being explicitly programmed for every detail? Today, we're diving into a groundbreaking new approach called BridgeVLA, which is revolutionizing how robots learn 3D manipulation using vision language models. Let's break it down. So what's the big deal with 3D manipulation? Traditional robot learning systems often rely on 2D images, like the photos your phone takes. But real-world objects exist in 3D space, and ignoring that structure makes learning inefficient. Imagine trying to build a tower of blocks using only a flat photo of the blocks. You miss critical depth and spatial relationships, right? That's the challenge researchers faced: how to let robots see and understand 3D environments as effectively as humans do. Enter BridgeVLA. This model bridges the gap between 2D vision language models and 3D robotic actions. Here's the clever part. Instead of forcing 3D data into a 2D format, BridgeVLA projects 3D information into multiple 2D images, like taking snapshots from different angles. Think of it as giving the robot a 360-degree view of an object, but in a way its AI can process. But how does this help the robot actually perform tasks? BridgeVLA uses heatmaps, color-coded images that highlight where the robot should act. For example, if the instruction is put the ring on the maroon spoke, the model generates a heatmap pointing to the exact spot on the object. This aligns the robot's input, what it sees, with its output, what it does in a shared 2D space, making learning faster and more accurate. The results? Mind-blowing. In simulations, BridgeVLA boosted success rates by up to 10% compared to previous methods. On real robots, it outperformed existing systems by 32%. And here's the kicker: it achieved a 96.8% success rate on 10+ tasks with just 3 training examples per task. That's like teaching a robot to cook a new recipe with just a glance at the ingredients. Here's the technical magic. BridgeVLA leverages a 2-step process: pre-training and fine-tuning. Think of it like learning a language. First, the model absorbs general patterns from massive datasets, akin to building vocabulary and grammar. Then it's fine-tuned for specific tasks, like ordering coffee or navigating a cluttered room. Researchers optimized hyperparameters, such as learning rates and batch sizes, to maximize efficiency. For pre-training, they used 8 A100 GPUs, but for fine-tuning, a full 48 H100 GPU setup. It's like upgrading from a bicycle to a rocket ship for the final sprint. Why does this matter? These models aren't just about speed, they're about robustness. Real-world robots face chaos, varying lighting, textures, and camera shifts. Projects like COLOSSEUM and GEMBench test how well AI adapts to these surprises. Imagine a robot learning to open a jar in a kitchen with flickering lights or a cluttered table. BridgeVLA doesn't just handle it, it thrives. Here's where it gets wild. BridgeVLA achieves 73.9% success on COLOSSEUM and 65% on GEMBench, outperforming other models by a mile. How? It's super efficient. In one test, it mastered tasks like close a box or insert a peg with just 3 examples. That's like teaching a robot to play chess by showing it 3 games. No wonder it's a game changer. Why does this matter? BridgeVLA isn't just a technical win. It's a step toward robots that can adapt to new tasks and environments with minimal human intervention. Whether it's assembling products, exploring disaster zones, or helping in healthcare, this tech could make robots smarter, faster, and more versatile. So what's next? As researchers refine these models, we're one step closer to robots that truly understand the world around them. Thanks for watching. If you want to dive deeper into the science, check the links in the description. Stay curious, and let's keep exploring the future of AI together.